So I have an exciting talk. We are going to look at computer vision, trying to see what are the different available ways right now in identifying either people or objects. You don't really need to know a lot about AI here. We have pre-trained and ready-to-use models right now, but we would also take a look at how do we even build a model in case we have to do that. A quick introduction, I'm Ravi Chandra. I'm a lead web engineer at 10up. That's my Twitter and LinkedIn in case you want to connect. I work for 10up. We are a web design agency. We finally craft websites and content management experiences using open source technologies like WordPress, React, Vue, and the other JavaScript frameworks out there. We are hiring. We are 100% remote, and feel free to check out our careers page. A quick look at the agenda for today. We'll taking a look at introduction to computer vision in general, and then we'll talking about convolutional neural networks, which is a type of neural networks which are usually used in image or video processing. And then we'll look at a quick introduction to TensorFlow.js. We'll also look at the Coco dataset, which is a ready-to-use, widely used dataset for classifying and identifying objects in images. And then we'll also build an object detection app using some of the pre-built models from Coco dataset. Then we'll look at MediaPipe, which is an exciting, great solution by Google, which was recently in beta, I believe right now. Then we'll look at, using MediaPipe, we'll look at building a person segmentation app. We'll also do a live demo of both these apps. Now, when we talk about computer vision, it's a field within artificial intelligence itself, which enables computers to understand visual information. It does that with use of different algorithms, different models, which are trained on a lot of existing images to classify objects and people. The primary goal is to replicate how we as humans, our visual system works. How do we see objects? How do we see things? How do we perceive them? How do we identify them? It's pretty widely used for object detection, image classification, facial recognition, and so on. Some of the key components of computer vision are image processing. Let's say we have an image. How do we process it? And then how do we extract the features within that image? How do we recognize the objects within that? Image segmentation and even motion analysis. It's widely used in autonomous vehicles. If you have ever tried any one of the autopilot vehicles, you'll see that it identifies all the signs on the road, speed limits, and so on. Computer vision, that's a real use of computer vision. We have medical imaging, security to auto detect, maybe if that feeds into your CCTV security or something, and it auto detects when someone is not supposed to be where they are. It's used in surveillance, retail, automation, industrial automation. We have these big manufacturing companies which are using computer vision to do some of the automation for quality control, trying to see if the production line meets the quality and so on. Now we are going to talk a bit on the convolutional network technical here. This is some of the boring parts. Bear with me here. So when we talk about a convolutional neural network, when we talk about a neural network in general in terms of AI, a neural network is pretty close to how the neurons or how the neural network works in ourselves, like in humans in general. We have a whole lot of neurons. We have different layers. Each neuron is connected to the next layer, and the neurons in that layer are connected to the next layer, and so on. We have an input layer, and we have an output layer, and the way that works, you feed it some input data. When you train it, it returns some random output, based on the output, you tell it if it's the correct output or if it is not. Based on your training data, it goes back in. It tries to adjust the weights on how these neurons are connected individually, and then there is also a concept of back propagation, where the results are also propagated back to the upper layers and so on. At a high level, that's how a neural network works. A convolutional neural network is a type of neural network where it's architected in a different way. We have multiple layers, so that each layer is responsible for different types of things, and we look at the four main layers here. We have the convolutional layer at the beginning, which does most of the image processing, and then we have pooling layers, which does some part of the data extraction, and then we have a rectified linear unit, which is also referred as ReLU. This is also sometimes this is actually an activation function. We will talk about more about activation functions in short. And then at the end we have fully connected layers, which is a generic neural network in general that is responsible to look at your look at the data from the previous layer and make a prediction. Now, just briefly talking about this convolutional layer, as we talked about, it is responsible to read the image and generate feature maps. That is responsible for extracting all the features in an image. A feature could be anything from either a color, either an object, either an edge. It could be anything in an image. Going back to the pooling layers, after convolution layer does its job, it sends that data forward onto the pooling layers, which is responsible to reduce some of the noise, only ensure that it keeps features or data that seem important. And then we have activation functions, which are used to, at least in a CNN, it's usually a ReLU, which is used to introduce non-linearity. We'll talk more about that when we get to activation function. And then we have the fully connected layers, which are, again, it's a normal neural network at the end, which takes all the processed image or the processed data so far and makes either a classification or a regression. Now, this is an interesting part. When we talk about a convolution layer, think of an image as a grid. Like when we say an 800 by 600 pixel image, it's nothing but we have 800 pixels at the y and at the x, and 600 pixels at the y, which is in a 800 by 600 grid. When we talk about a convolution layer, what it does, it's also a grid, but probably a smaller grid, maybe a 3 by 3 or a 5 by 5. When it starts processing at the image, it starts at the top left, and it keeps on, it does a sliding algorithm where it keeps on sliding across all the, from left to right and then top to bottom, ensuring that each pixel in the image is covered. And when it does that for each of these either 3 by 3 or 5 by 5 grid, it does some sort of a mathematical calculation, which again depends on some of the factors when we build the model. At the end of the convolutional network, what it does is it creates another grid of pixelated image, where it tries to maybe highlight some of the edges, or maybe some of the colors, or maybe some of the shapes within the image, which is more significant for computers rather than as humans. So we can see that it creates a new map with different patterns in the picture. And again, there are different types of convolution layers we can build. Some of them look for different patterns, some look for different patterns, some might look for edges, some might look for others, and so on. And once we have the convolutional grid created, it passes that new grid onto the next neural network. And we have a great example here. We have the source there, which actually talks about convolutional layers in depth. It's a pretty good read. And if you look at the first image here, we have an input image. Think of that as when you talk about image, right? We talked about a grid, and each value in the grid is nothing but a representation of the RGB color, either 0 to 255, the hex code, the RGB code for that pixel itself. So when it starts at the top, we have a 6x6 image here. We are doing a 3x3 convolutional layer. It starts at the top. It looks at that first grid there. It does some math calculation. It gives them weights based on what it finds, and then it comes with that number 429. And it continues that process. If you look at image 2, we can see that it keeps on doing that sliding function with that math magic, and at the end of the by the time it looks at the entire image, we have at the right we have a small image with a different number, which is an extracted image with specific features. And let's talk about pooling layers now. We have this convolution layer which looked at our image, picked up foreign parts of the image, and sent it to the pooling layer. The pooling layer does more filtering on it. Maybe there is more noise, maybe there is more whiteness, there is more saturation, there could be a lot of things. Pooling layer ensures that it drops all those. It ensures that it only picks up what it feels is most relevant to do any sort of classification, and then it just gets rid of data or noise, and it passes that on to the next layer. And then we have an activation function. This is not a layer in itself. It's used to be calling as a layer, but it's not a layer in itself. It's a mathematical function. We have different functions, different type of functions on how we want to activate a neuron or a layer. But the one widely used for in a convoluted neural network is ReLU, because it ensures that there is no linearity when it identifies these images, because images are not always black and white. They are never linear. They have to be non-linear. You have different patterns. You have images are like pretty complex. ReLU ensures that there is non-linearity, and we are not focusing on maybe one part of the image which is too bright or one part of the image which is too dark. And it also helps build complex non-linear relationship between in the model between the neurons. And the last layer is the fully connected layer, which is a basic neural network layer which accepts the output from the pooling layer, reads it back, and based on the extracted features, it makes some meaningful decision or a prediction. Again, this image is from the same article, which is an excellent introduction for CNN. We see that we have an image at the beginning. We have the convolutional layer, which looked at parts of the image, did some extraction, passed that on to the pooling layer, and which is a big image is trimmed down to maybe half of its size or 20% of its size. It depends on how we set up the model there. And at the end, we have the fully connected layers, which take the features or the image which only has the features, look at that and make a classification. In this example, it would try and see if it's what are the objects in this image. Is it a dog? Is it a cat? Is it a boat? And so on. Yeah.
What does that axis that way mean? I see one image on the left, but what are the next side? There's three big squares going that way. What is that mentioned?
That's the layers within the network itself. So the first one is a convolutional layer. So when we talk about neural networks in general, I probably have an image somewhere, but when we talk about neural networks in general, we have like different layers stacked on top of each other, and we have data flowing from one way to the other. That is exactly what's happening here. In the first, we have the image, and we have a convolutional layer, which looks at the image, trims it down, sends it to the next layer, which does more processing and sends it to the next layer, and so on.
So it's a layer of three layers.
It's not 3. I wouldn't say it's 3. It's probably more than that. Again, it doesn't have to be 3. It depends on how we build the CNN model ourselves.
I will slow you down.
Let's look at TensorFlow.js. Even though we won't be building any models ourselves, we could definitely look at how we can do it ourselves. So TensorFlow.js is a machine learning library for JavaScript itself. You can build your own machine learning models either in the browser or in a node environment, or you can also run existing off-the-shelf JavaScript models, which we are going to do today, and we can also convert existing Python TensorFlow models. And you could also retrain if maybe there are some existing ML models, but you want to retrain that with your own data or with your own context. You could also do that. And if you go to TensorFlow.js/models, like all these models are already available. We could just look at how to start using them, and you can start using them within your JavaScript application in the browser. We have image classification, object detection, semantic segmentation for body, face detection, face landmark, pose detection. We even have for text, natural language questioning answering. A good, probably not as good as an LLM though, but probably for your entry level chatbots. And then we have the text toxicity detection, which is used to identify spam or any sort of comments. We also have speech command recognition. Now let's talk about the COCO dataset, which stands for Common Objects in Context dataset. This is a widely used dataset for computer vision. It's nothing but some terabytes. I don't even know how many images there are. There are different datasets. There are like terabytes of images which are already created, which are already marked. I'll show you how they are marked, but these images, using those, you can build your own computer vision model. You can train that on the COCO dataset, and based on what you're trying to do, you can train it, and you can see how it performs. This is an example of an image in the COCO dataset. As we can see, it's a normal image, but some parts of the image are tagged in color, like the monitor over there, the keyboard, the mouse, and the laptop. And the way this works, for each image has extra metadata or maybe an XML file in the dataset itself, which tells it, okay, in this image, starting at this pixel, ending at this pixel, we have a monitor, and starting at this pixel, ending at this pixel, we have a keyboard, and so on. So when so you have an image, you have the output, you have the image, you know what the output should be. You send it to the model you build, and if the model tries to train on it, and if it makes a mistake, you tell it what the loss or what the accuracy is, and you keep on repeating that training process until you see a better performing model. So for us, today we are just going to use one of the pre-trained models, because training a model on COCO dataset, or even training a model in general in the browser is pretty expensive, because not expensive, there are also some limitations because of having access to the file system or some other stuff, and even due to some of the performance implications. Python does a pretty good job because it works directly on the operating system. So for our first example here, what we would do is we would use TensorFlow's COCO SSD, which is an already built and trained model using the COCO dataset. You can see, you can find that model in there along with how to use that, and we'll use that to do some real-time object detection. This is a good model. This is just a start. This is just a entry-level model. You can't really use it for accuracy. When we go to media pipe, we'll talk about media pipes object models too. So this is a repo which has most of the examples I'll also walk through now. And it also has, if you just clone that repo, you can actually start running both the object and the person detection apps which you're going to build. Now using the Coco SSD model, it's pretty simple. You either do an npm install or you just include those two those two JavaScript hosted on CDN. Now to use the model, we call the load method of the Coco SSD global object itself. It gives you an instance of a model. The model has a detect method which can either accept a TensorFlow tensor, or at least for the web, it accepts image data object, image element, video element, canvas element. So you can just pass, let's say you have an image in the HTML or something, you have an image element, you just get that element and you pass it on to model.detect. And what it returns is a list of objects that are detected in the image itself. And we can see it's a list, and each item is an object with the properties bbox, class, and score. Class is what it thinks the object is. Score is how accurately it thinks it's that object. And bbox is the bounding box. It's your x and y parameters of the position of that object in the image. And then you have the width and height. Using that, you know the x and y, and you know the width and height, you can probably identify where that object is located. Now let's use that and build a real-time app here. So what we are going to use, this is all in the browser. So we are going to use HTML video, canvas, and vanilla JavaScript. We use the video so that we could read the camera of the computer itself, and we use the canvas so that when we pass that video feed onto the model and it gives us back the objects detected, we can use the canvas to paint probably a box or a rectangle around that object. We would also use Media Devices API to gain access to the webcam. So we start off with attaching the camera stream to an empty video element so that we could feed the actual camera stream to the video and we can play it real time. And then we pass the video element to the Coco SSD model detect method. As we have seen before, it can accept an image and it can also accept a video element. And if you pass it a video element, it predicts. It does not do a live prediction. What it does is it gives you the objects it identified for that exact frame when you call the detect method. And once we pass the video element and once we have a list of objects we have identified, we will draw each of them on the empty canvas with a label, and we overlay that on top of the video element. And we use a request animation frame to call the detect method for every repaint. So starting up with the HTML markup, which is pretty simple, we have a wrapper div with the canvas and a video. And the canvas is used just for us to mark those objects, and video is where we play the actual live feed. Again, some more helper methods to set up the camera feed onto the HTML canvas here. We use the Media Devices API, we enumerate it, we look for video input devices, and here we are just like trying to make an assumption that the first video input device is your camera, which is probably not the case, and we might need to, if you're doing it for real time, you need to ensure that you account for other video inputs too. And then we pass the device ID onto setup camera, which again sets up, if we look at the video config, it sets up, we don't need the audio, we just need the video with the width and height with the device ID, And the frame rate, we are trying to limit the frame rate here just for demonstration purposes and ensuring that we have a smooth, because for every frame update we are sending that to the model and we are waiting for it to make a prediction just to smoothen things out. We are limiting that, but this is not really required. Maybe you have a better processing power, you could increase that frame rate too. And in terms of the stream, we again use the media devices API, call the get user media, pass on the video config, and then you have the stream of your computer's camera. And then we get an instance of the video element itself, set its source to the stream, and we once the metadata is loaded, we just start playing it. And so that's how we set up the camera. And going back to the Coco SSD model, we are using in our run Coco method, we are again, we talked about this briefly, we are loading the model, and in the predict method, we are running detect on the model, and then we are calling the predict method again for the next frame repaint. This ensures that whenever the video keeps on streaming, we are calling the Coco SSD model's predict method for every frame update. We haven't looked at the detect method though. Yeah, so this is the detect method. It checks if the video is ready. It does the width and the height. It's done to ensure that we have both the canvas and the video at the same width and height, and ensuring that they are overlaid on top of each other. The actual detection happens at model.detect video, and then we have the results in the obj in the obj constant there, which we pass it on to draw rect, which I will take a look here. So this takes the detections, it iterates through all the detections, reads back the XY width and height from the predictions bbox property, reads the actual classification of the object from the class property, and then it does two things. One, it draws a rectangle around the object itself using the XY width and height, and then it draws a label at the top of the object. And we can take a look at the demo here. As you can see, it did identify me. Let me try the cup here. Yeah, the lighting is not that good, but yeah, it does identify a cup. Again, the Coco SSD model itself is limited to like 80 or 90 objects. It cannot identify all the objects. Yeah, it does identify a phone. I also have a book, which I think it should be able to identify. No? Yeah. So again, this is a pretty simple Coco SSD model. We have better object detection available in the media pipe, which we'll talk about shortly. Yeah, so let's talk about media pipe. Media pipe is a open source framework. It's by Google. It provides a comprehensive set of tools and libraries for building applications that require audio and visual data. Some of the Google applications that use media pipe, Google Meet is a great example. When you present yourself, when you are on camera, like all the features you see part of Google Meet are driven by media pipe, and it's primarily focused on development of real-time cross-platform solutions for computer vision, machine learning, and signal processing. So you don't need to know any of the convolutional neural network or like trying to wrap your head around it, you can just start using media pipe, and you can integrate any cool AI solution if you have a need for that. And it is designed to be efficient, scalable, flexible, in wide range of applications from either mobile, web, or even desktop software. Now, MediaPipe has a model or a solution which is called as selfie segmentation. What it does is it's mainly designed when you either take a selfie or maybe you're on a video call in front of your computer. It's intended to ensure that it can identify or mask the person from the background, so that you can do some cool stuff. Maybe you're taking a portrait type of picture in your camera and you're in your selfie mode. It ensures that like you are always in the focus rather than the background. Now, using the selfie segmentation, we import that as a model, and then we call the selfie segmentation class. We pass a parameter to locate the file. This is required because it's not. Some of these models are humongous. I believe selfie segmentation was around 30 megabytes or something. So it's not one single file. It batches that. It puts them in chunks, and only when you actually load the fully model, it makes asynchronous request to load all these files. So this locate file is we telling it where to load each of those individual files from. Probably we have our own CDN or maybe a private network or something. We could always change this to ensure that it loads from our own network. And set options, we are just setting some options here, what type of a model we want to use. And then on results is where we pass a callback function, which is triggered every time the model makes a prediction and has some results for us. And once we have the callback and everything hooked up, we do .send of the selfie segmentation model, and we pass image. That's the name of the parameter. But the value can again be an image, it can be a video, and I believe it can even be a bitmap image too. And the result from the result which our on results callback receives is just one object with two properties, image and segmentation mask. Image is again what we have inputted into the model itself, and segmentation mask is where it gives you an image bitmap with which actually masks the people in that image. And this is an example of a segmentation mask. So when you're looking at the camera and you take that image and you send it to that model, it removed all that background and it was able to identify the person in the image itself, and that is the mask it sent back as a result. Now let's build a person segmentation app. What we want to try and do is something Zoom or even I believe Google Meet does that now. What we want to do, we want an app that can use your computer's web camera and only keep you in the focus. Maybe blur out the background, maybe switch the background to some cool place rather than your boring office or home. So let's see how we can do that. We'll again use HTML video, Canvas, JavaScript, Media Devices API. Most of the camera setup we have done in the previous demo, we are going to reuse that. But instead of using that Coco models in the past, we would do a media pipe selfie segmentation, and we send that to the send method with the image parameter, and we attach an event listener to the on results method, and we again use a request animation frame to call the send method, so that on every repaint we send the video stream to the model. And because it only returns a segmentation mask, we need to do some canvas painting techniques to ensure that we take the segmentation mask. We have our own original image and we overlay it on top of that in such a way that we only keep the person and we just blur everything out. And setting up the model, so some of this we have already looked at. The major changes are after we call the selfie segmentation.send, we are again doing request animation frame and we are calling the same method itself so that it keeps it keeps an infinite loop and we keep on getting live results. And let's yeah, so on results we have called blur background here, and if you look at blur background, again this is mostly setting up the canvas, ensuring that the width and height are same and everything is in sync. So this is where we do the painting magic. Initially we just draw the image we get from the model itself, the original image we have sent it. We get that, we just draw it on a canvas, and then we use a compositing technique called as destination in, and we use that technique with the segmentation mask. What that gives you is just the person but no background at all. So you will see you'll see an empty canvas with probably a white background or a transparent background and the person itself, but we want to have a blurred background. So what we would do is we would again do some additional techniques. We create an empty canvas somewhere on the page which is not even used anywhere. We take our original image, we blur it down like 15% or something. We draw our original image on that canvas, and again using the compositing technique, this time we remove the person but we keep the background, and at the end we bring both of them together. So you have the first image with the person, no background, and then you have the second layer with just the background, no person, and it's fully blurred. Let's take a look at a demo here, and as you can probably see, the lighting's bad here, but as you can probably see, the background is kind of blur, and we just have the person in focus here. I can also show you a couple of things. If I just draw the mask I get from, so this is the actual segmentation mask with no canvas techniques itself. So this is what, like that green mask is what the model is returning here. And yeah, some of the other resources you can look at to start looking at the existing solutions and see if something interests you. I also want to take a quick look at MediaPipe. So this is a code pen from MediaPipe which is in the resources, and you can see there are some pretty cool examples they have done, like a face mesh, or even there is a pose detection. Yeah, I think it's having some issue. Yeah, as you can see, it can identify my pose, and yeah, this is all part of MediaPipe. Yeah, and then we also have the Coco dataset .org. You can go explore what it all has and look at the different datasets, and yeah, so you can also look at some of the cool stuff we can do with the segmentation. Yeah. And that brings to the conclusion. Thank you.